In this video, we're going to be talking specifically about the geometry of cycloalkanes. So, unlike linear alkanes, cycloalkanes adopt very specific geometries in order to minimize the energy of their conformations. Now, we saw that in doing conformational analysis, something like a linear alkane is going to adopt this zigzag structure so that every point along the way is going to have anti-conformations when we look at the Newman diagrams. However, the problem with cycloalkanes is we don't have this freedom of rotation in a cyclic structure. The bonds can only rotate so much before we start breaking bonds or straining the bonds beyond the point where they can stay attached to adjacent atoms. So if we look at the various types of alkanes, we have cyclopropane, we have cyclobutane, we have cyclopentane, and then we have cyclohexane, and these are the main ones we talk about in organic chemistry. And we'll see that based on geometry, these should all be planar. Based on just the geometry of shapes, these should all be planar. I'm going to actually make this a little bit more accurate. So based on geometry, these should all be planar structures, and we can calculate the expected bond angle by doing just some basic math and getting that this is expected to be 60 degrees, this is expected to be a right angle at 90 degrees, and so on and so forth. However, these are planar, but they're also all sp3 hybridized carbons. And what we know is that sp3 hybridized carbons prefer a bond angle of 109.5 degrees. So, for instance, if we look at a 60-degree angle expected in a cyclopropane and compare that with the desired bond angle of 109.5, this leads to some very unstable circumstances. And unless we can alter the structure from this planar conformation, then we are going to run into some issues. So there's a couple different kinds of strain that we encounter in cycloalkanes. One of them, which is what we just talked about, is going to be from the bond angle. So this is bond angle strain. So bond angle strain is strain caused by deviation from the ideal. And in the case of cycloalkanes, the ideal is going to be 109.5 degrees. So anytime we get away from 109.5 degrees, we're causing bond angle strain. And the further away we get from that, the more bond angle strain we're going to experience. The next one is one we already saw in conformational analysis, is we can have torsional strain as well. And this is strain from eclipsed bonds. So in a planar structure, all of the bonds are going to be eclipsed. So this is going to create a great deal of torsional strain, which we can alleviate by twisting out of the plane a little bit. And finally, we're going to have van der Waals strain or steric strain. And van der Waals or steric strain is caused by bulky groups. Bulky groups close together, and we saw that in the differentiation between various eclipsing fashions of the rotation of butane. We see that when we have eclipsed big groups, it's going to have a large degree of steric strain. When we have eclipsing small groups, it's still steric strain, but smaller. So let's go through all four of these, cyclopropane, cyclobutane, cyclopentane, and cyclohexane, and examine how we can minimize these three types of strain in order to have an ideal structure. And this will be key when we're talking about the actual structure of these different types of cycloalkanes. So let's first talk about cyclopropane. So cyclopropane, this is going to be CH2, CH2, CH2. Cyclopropane is very unstable. As we demonstrated a second ago, that this planar angle is going to be 60 degrees, which is very far away from the 109.5 degrees that's desired by sp3 hybridized centers, which all of these are. So there's a large deal of angle strain. We also see that if we draw this with kind of or not stereochemistry, we draw this kind of with um, 3 dimensions. So we have 3 H's pointing up, 3 H's pointing down. Um, if we were to look down any one of these bonds, say look down this bond, we would see that all of these hydrogens are eclipsing one another. So not only does it have high degree of angle strain, but if it's got very high degree of torsional strain. So as a result, this is incredibly unstable. So cycloprocane is very unstable. And you can imagine that if we start tacking on groups to replace these hydrogens with larger groups, it gets even more unstable because we start experiencing larger degrees of steric strain and van der Waals strain. So cyclopropane, very unstable. Let's move up to cyclobutane. So cyclobutane, again, it's got H's all the way around. Cyclobutane is 4 carbons in a cyclic structure. All of these are sp3 hybridized, and if we look, this planar structure expects a 90-degree angle. This is much better than having a 60-degree angle, but it's still quite a bit far away from the desired 109.5 degrees. So there is some angle strain. It's better, but it's not perfect. So what happens in order to relieve some of this strain, if we draw this cyclobutane with some geometry, we'll see that if it's planar, all of these H's are pointing up, these H's are pointing down. If we look and if it's planar, we see that all of these, similar to the cyclopropane, we get all eclipsing interactions, so we would have a high degree of torsional strain. So what happens is the cyclobutane ring puckers a little bit. So it puckers. There's some amount of rotation, so some degree of conformation, and we get instead a structure that looks like this. So you have an H pointing up, H pointing out and pointing down, and out and down. So we call this a clamshell structure, as it kind of looks like a clamshell. And what we'll see is now, if we look down one of these bonds, say we're looking down this bond here, we have staggered conformation between these bonds. So this would be all staggered. And that's going to be much more favorable. It reduces torsional strain to almost nothing. So we do have some angle strain, but the torsional strain is being reduced by adopting this clamshell conformation, such that you get staggered conformation between the H's. This is also going to reduce any potential van der Waals strain. So you can end up getting substitution on various positions along the cyclobutyl ring because of this structure that causes them to be staggered. So the next one, we're going to add one more carbon. We're going to keep moving along. Let's look at cyclopentane. So cyclopentane, I'm not going to draw on all the H's. The angle in cyclopentane, if you do the math, just geometrically, is going to be 108 degrees, which is almost 109.5 degrees. So you can imagine that a planar structure of cyclopentane is possible. However, just like all of the other planar structures, so again, this is saying almost no angle strain. But just like the other planar structures we've seen, if we have planar structures, we end up getting all eclipsing bonds, and that's going to be unfavorable. So in order to relieve the unfavorable eclipsing, the torsional strain, we get what's called an envelope conformation from cyclopentane rather, which kind of does something like this. So you get H's over there, you get some H's over here. Now there is some amount of eclipsing strain that goes around, but it's much, much less than it would be if this was a planar molecule. So it adopts, we call this an envelope conformation. And you can imagine that this point here could be any one of the points around the circle. So this is actually flying around. This is moving around at very fast speeds. So the what happens is the torsional strain uh, is almost zero. So cyclopentane is a very stable structure because it has almost no angle strain, and by adopting this rapidly spinning envelope structure, the torsional strain is also almost zero. And for the final one, let's examine cyclohexane. So we'll be seeing a lot of cyclohexane in this course and in the following course if you take 252. Cyclohexane, again, if it's planar, um, it's going to have a lot of eclipsing interactions. So we want to somehow twist it out of the plane to reduce the torsional interaction. And it turns out that the most stable conformation for cyclohexane is called a chair. And the way we draw a chair is we take two parallel lines, we put them across from another, we make a V, and then you make another V. I'm sorry, that's a let me make that a little bit better. I'll make these lines a little bit longer. We make this. There we go. So this is what we call a chair conformation. And a chair conformation, there's two different kinds of hydrogens. We have some that are pointing up and down, and you'll know whether it's pointing up or down based on where this point points. So this vertex points up, so this is going to be an up hydrogen. This vertex points down, so it's going to be a down hydrogen. We have another up, a down, an up, and a down. We then have some that are going to be pointing, finishing this tetrahedral structure, and they're going to be pointing in the plane of the cyclohexyl ring. So we kind of draw them at an angle to indicate that it is sp3 hybridized. And I'm drawing these different colors because these have different names. So these blue ones, these ones that are kind of flat, we call these equatorial. The ones that are sticking straight up and down are called axial. Now there is an alternate structure for that relieves the torsional strain that's a little bit higher in energy. So if the chair is the lowest in energy, the next lowest in energy is called a boat. It is called a boat because it kind of looks like a boat. In this case, it is again reducing torsional strain, but not all of it. So it's not the ideal structure, but is a possible structure. If we had to choose between these, we would choose the chair conformation because it is the most stable conformation. But boat is along the way to chair, and we'll see where this boat comes in a second. So boat is less stable, and chair is going to be more stable. So a unique thing about the chair, now we've seen, what I mentioned in the beginning of the video is that the problem with these cycloalkyl structures is they cannot really do free rotation, and that's because it would end up breaking bonds if they could rotate all the way around. A unique thing about cyclohexane is it has a large, wide degree of rotation that's possible, enough to actually have a couple different structures that manifest out of the chair conformation. So if we draw our chair conformation again, I'm going to label my axial hydrogens. Just bear with me. I'm going to label my axial hydrogens again in red. I'm going to label my equatorial hydrogens in blue. There's a great deal of rotation that can occur about each of these bonds. And in fact, we see that if all of the bonds rotate a little bit all at once, we get what's called a ring flip or a chair flip. The way to draw this is we would kind of do the reverse of this. If we have the point on the right, we would put the point on the left. And what we notice is that the axial and the equatorial hydrogens are going to swap places. So everything that was axial in the original ring is now going to be equatorial. So those red ones have become equatorial, and the original the original equatorial hydrogens, the blue ones, are now going to be axial. And this is characteristic of a ring flip. We see that exchange, so you exchange axial and equatorial. And this is going to come into place when we start putting substitutions on the ring. As it stands, there's no preference between these two because they're all hydrogens. However, when we introduce non-hydrogen substituents on the cyclohexane ring, we do end up having a preference for one chair conformation over the other, and we will see this in a future video.